Hello everyone, our topic is binary heap and I am Amol Bharadwaj, registration number 943. Priority queues. Binary heaps are especially useful data structure used in a variety of contexts. But why would we want to use on how do they work and what problems do they solve? To answer these questions, let's start with a problem. Let's say you have some tasks to complete and each task has a priority, some number representing the task important, one for your most important task and two for the next tier of importance and so forth. You want to organize tasks such that you can easily access your most important task first. This way of organizing data is called priority queue of collection of values, where at any time we always want to access to the most important item. How would you store this data in a data structure? You could use an array sorted by priority that makes it pretty quick to access higher priority items, but with a fixed size array, you'll run into trouble. If you ever need to add a new element into your priority queue, there's no space for another item. Another option is a linked list with each node of data pointing to the node that follows it. This strategy makes it possible to add new data by rearranging these pointers, but still not so efficient to add new data. We might have to look through the entire linked list just to find the right place to add our new information. This is where binary heaps come in.
Hello guys, my name is Praveen Kumar Singh and my registration number is 944 and I am going to speak on the topic binary heaps. Binary heaps also consist of the nodes of the data, but they are structured as a binary. That means instead of each node of a pointing to a single other node, nodes can have up to two so-called child node. A left child and a right child node is allowed to have no children, just a left child or both have a left and right child. Each node in a binary heap also obeys an invariant, in other words, a property that will always be true in a binary heap and in a particular a type of binary heap called a min heap. The value of any node must be less than or equal to the value of its child node. Why is that important? Well, this means the node with the smallest value must be at the top or root of this tree. So, with this structure, it is easy to find the minimum value node just by looking at the root of the tree and ignoring everything else within this binary heap. There are two common operations we'll likely need to perform. The first is insertion, that is, adding a new node to the heap, as we might do if we have some new task to complete. The second is deletion, that is, removing whatever is at the root of the heap, as we might do if we have completed the highest priority task. So let's start with the insertion. What do you mean by the insertion? When we want to add a new value to a binary heap, there are two factors we all need to bear in mind. First, what is the first? What the shape of the new binary heap will be, and the second one is preserving the heap invariant that nodes are never greater than their child. Before we think about the heap invariant, let's ignore the actual value associated with these nodes for now and just think about the shape of our heap. Remember that each node can have a left child as well as a right child ideally. We want the left and right side to be balanced with an equal number of the nodes without an imbalanced proper shape on each side of each node. Since if the heap is imbalanced, it might be less efficient to work with. But depending on this factor, if there were an even or odd number of the nodes in the heap, it might not always be possible for the heap to be perfectly balanced.
Asmi Sharma, 971. To account for that, we will allow nodes. You have one extra node in the left subtree, then in the right subtree. This gives us a pattern for what the shape of every different size binary heap should look like. With one node is just the root, the second node we add to the left side, the third node gives to the right to keep things balanced, the fourth node needs to be the leftmost node since we add to the left. First, before we add to the right, the fifth node must be the child of the third node to keep things balanced again. The sixth and seventh nodes then fill in the last blanks in the left first, and then right, the eighth node would be the leftmost node of a new level of this tree, and so forth. Whenever we add new nodes to the heap, we need to preserve this kind of shape. But if we just take new element and add to the bottom of the heap in the right place, the heap invariant will often be broken the parent might be greater than the new node, for example, so will likely need to make some adjustments to this heap to ensure that it follows the heap invariant. We'll do so by repeatedly applying a rule compare the node we have just added to the parent. If the parent is greater than the node which isn't allowed in a binary heap, then we need to swap the node with its pen. Once we make the swap, will you repeat the process. If the parent is greater than the node, then we swap the two. Once we've reached a point where the parent is no longer greater than the child, we can stop. The heap invariant is now satisfied. In the worst case, we might add a node that's smaller than every other node in the heap, and in that case we would need to make swaps all the way to the top the heap, but often that won't be necessary, and we'll just need to make a few swaps before the node ends up in the right place. We now have the ability to add a node to the heap.
Hamza Iqbal, and my registration number is 953. The other actions we'll want to perform is deleting a node from the binary heap because the binary heap is designed to give just us access to the minimum element. That's the only one we are allowed to delete. But once we remove the node from the heap, we are left with a heap that it is correct shape anymore. In particular, it's missing root node. So how do we fix the problem? As we did with insertion, let's first get the heap in the correct shape and then worry about satisfying the heap in the variant. That element can be greater than their children. To get the heap into the correct shape, we can take an element from the bottom layer of the heap and move it to the new root. Remember that we need to preserve the rules for the shape. So if there's an unevenness on the bottom layer, we should remove a node such that the balance the heap, and if it's already even, we should remove the right side first before we remove from the left. Of course, we move the last element to the root of the heap. The heap invariant will likely not to be satisfied anymore. The new root is probably going to the greater its children. So now do we repair the heap similarly to do? We did so with the insertion. When we were inserting into the heap, we made swap starting at the bottom and moving upwards. Now we'll make swap starting at the top and moving downwards. If the node is less than or equal to both of its children, once we are done, we don't need to make any more swaps. Smallest child and make the node new root, so we'll swap our node with the smaller child and repeat the process. Swapping a node with the smallest child again and again until we reach a point where we either hit the bottom of the heap or the node is less than or equal to both children. At this point, the heap will have the correct shape and we'll make all the necessary corrections so that the heap invariant is preserved. So now we have a heap that is slightly smaller with the new smallest element at the root. With its ability to add element and remove elements from the binary heap, we have all the pieces. We need to implement our priority queue. As we get the new task, we can add them to the heap. We can quickly see the most important task and then we can remove it once it's done.